Hey, Chem 110 students, we've made it through week 6 and are into week 7, and we only have a total of 11 weeks of this course, which actually includes finals week. So as you can see, we're kind of on that downward slope to getting to be like, woo, we're all done. So I'm excited. I got my orangutan earrings on that I made, and I'm ready to go. So let's talk about week 6. So to begin with, some highlights from the week. First of all, just continued resilience and survival. I know it's spring quarter, and it's spring quarter in what has been a really long year. And so it's hard to kind of keep going, but keep it up, and most of you are doing great. And always communicate with me if you're having trouble or you need some help or you have questions, all right? Another highlight of the week for me is that best lab selfie competition that you participated in. If you participated at all, you got extra credit. And I did knight a winner. Congratulations to Ariana. I did not ask permission, so I didn't put her selfie in here, but anybody who can include a chicken in their selfie, I think gets definitely extra credit in my heart, but also like literal extra credit for the competition. Also, her chicken's name is Hey Hey, which I think is also worthy of extra credit. So I really like chickens, and so that kind of won me over a little bit. So congratulations, Ariana, and thank you for all of those of you. I really enjoy your lab selfies overall. It's just nice to see your face. It's nice to see you doing science, and it reminds me that you're here and you exist and you're a real person. So we only have, let's see, 7, 8, 9, 10. That was a weird way to count. We have 4 labs left, so that's 4 more selfies that I get to look at. So keep them coming and keep them good. I love the people who just kind of make me laugh every week for various reasons on your own, not even a competition. So our discussions from this week, we're really going to be talking a lot about water in both last week, week 6, and then upcoming in week 7, and almost even in a way for the rest of the quarter. So in terms of that, we're looking at phases of matter, because we're all pretty familiar with all 3 phases. Water exists in all 3 phases in the universe. It's not necessarily the only substance to do that, but it's definitely the first one for me that comes to mind. So then since we're looking at phase changes, this is a good time to introduce the idea of endo and exothermic changes, because a chemical reaction can be endo or exothermic, so can a phase change. So focusing on water and some of its awesome properties, and we'll be continuing that with week 7, so you'll notice a lot of carryover in concepts, which is nice, because then you're like, oh yeah, I really know this already. So let's talk about this question. When scientists look for life on other Earth, they actually don't look for evidence of life first, they look for evidence of water. And that is because they believe that no matter where they go, that there has to be water in order for there to be life on Earth. And so the question is like, why? So the book talked about 2 real specific reasons, so let me kind of highlight those in 2 different students' response. So first of all, we have Leslie here, who kind of draws straight from the book, which I like. You should always provide evidence for your reason, and so in this case, we're kind of citing our source. And it's totally fine in this case to just say the textbook. You don't have to do any like APA citation, because we all know what book we're talking about. Our body counts for 60% of the total mass. That isn't true of all organisms, but it is believed that water is required for life for all organisms, no matter if we're talking those giant trees that we looked at last week, or humans, or little tiny single cells, because of its molecular structure and special properties. So Leslie here gets into the first reason that water is believed to be required for life, and that is because it stays in the liquid phase really well and for a really long time. And so liquids have molecules that are able to interact with each other smoothly. They bump into each other, and they're constantly moving around, which is necessary for all of those chemical reactions that we need to happen in a living thing. There's a lot of chemistry that needs to happen, and if that was trying to happen in the gaseous phase or in the solid phase, it wouldn't happen fast enough for most things to survive, so that's a big part. And then of course, water isn't the only thing that's liquid at the kind of normal temperatures on Earth, so that alone isn't. Another factor, which Miles gets into here, is that because of the nature of water, lots and lots of substances can dissolve into it. Not just 1 or 2, like, oh, this can dissolve in water, but this can't. Lots and lots. Water is obviously not a universal solvent, because that's impossible, but it's been called the universal solvent because so many things can dissolve into it. And that's really important to support the diversity of molecules that we would need for those chemical reactions here that Leslie is talking about to occur in the liquid phase. Now, I really want to clarify here a little bit, and allow me to tease you all a little bit. I have a silly personality that hopefully you know by this point, and I do like to tease, but please understand it's coming in jest a little bit, and that I wrote this meme for you guys. I don't always do the assigned reading, but when I do, I know what's going on. For me, this week, it's always really clear who did the assigned reading and who didn't, because I get a lot of very interesting answers, some of which are still really accurate. But this question really is one of those, it comes right from the reading. And so if you're not doing the assigned readings each week, you really are missing out on some important information for the course. You're also missing out on utilizing some different parts of your brain that are going to help with memory consolidation. And you're also, in my opinion, again, this is just, you're hurting yourself for that open book, open note test, because if you haven't done the reading, you're not going to have a very good idea where in the book certain things even are. Not to mention our book has some really cool features for you can like bookmark some stuff. So you can be like, I need to find this page during the test. So I would really encourage you all to do that assigned reading, because it's going to help you out in the long run, especially for our exams. And also because then when I'm looking for, did you demonstrate understanding, it's a little bit easier for me to tell of like, this isn't really an opinion question. This is one of those like from the book things. And we're going to have another one of those coming up. So do make sure to do your assigned reading as is expected in the course, right? All right, so let's move on. This is such an interesting sentence. It is not so much that the ice in your cup is cooling your drink down, but the drink is warming your ice up. And so I wanted to highlight Grace's response here, because first of all, she got right away that melting, that physical change of melting is endothermic. So that means energy goes into it. So endothermic means energy goes into it from the surroundings. Well, if the surroundings are losing energy, their temperature is going to change, right? So the ice in the water is absorbing heat from the water, which makes the water, the surroundings, cold. It's weird. I totally agree, Grace. It's weird to think that the ice is getting warmer, yet your drink is getting colder, but that's exactly what's happening with the direction of heat being spread out, blah, 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 blah. Anyway, interesting thing to think about. So next time you have a drink and you put ice cubes in to cool it down, think about that energy transfer that's happening. It's kind of fun. Chemistry is everywhere, right? Great thing to include maybe in your final project if you happen to be including something where you can focus on endo or exothermic changes. One thing I do want to identify, because I'm seeing this language a lot in our discussions, objects cannot be endo or exothermic. You cannot, that's not a classification. Endo or exothermic isn't a physical property. Changes, so that can be physical changes or chemical changes, those can be endo or exothermic. So just to clarify there. Moving on, I love this video. So let's talk about Troy's response here. Troy was one of the only students to even address this, so thank you for that, Troy, among other things. So I mentioned in my initial response the balloon is attracted to a string, but looking back, it actually isn't a string, it's a fine stream of water. So I would now say that the charges in each vary, and the water has positive and the balloon has negative, and this is a really critical sentence here. Positive and negative charges are attracted to each other. So this is a demonstration that's really showing us the polarity of water. So remember, water is polar. That's so important. Water is polar. Now, water is not negative or positive. Water molecules are overall neutral. But due to that polarity, water does have a partial positive side and a partial negative side, and we can prove that with a balloon. If you rub a balloon on your head, you strip electrons from your hair and give the balloon an overall negative charge. And so we are attracting the positive in the water. But I do want to clarify, water is not ionic and water is not only positively charged. In fact, I wouldn't even say water is fully positively charged. It's partially charged. So it's like a little bit charged. And that's why we use those kinds of terms in terms of it. It's being polar, not ionic. So excellent demonstration. I love this one. There's a number of other demonstrations online on why water, to prove water is polar. If you have like nothing else to do today, you can go look. So this is a good one to show that water is polar. If we were able to put a non-polar substance in here, we probably wouldn't see much movement in the liquid. So if we put like liquid hexane in here, which is a hydrocarbon, and by all hydrocarbons are non-polar, and we rubbed the balloon on our head and moved it toward the stream of hexane, I don't think we'd see much movement, if any, at all, because we don't have any of those partial positives and partial negatives. We really get, with that even electron distribution, we don't have any area of positivity or area of B negative. Which actually gets us into this next one. We're kind of already talking about this. This comic is about water's polarity, and some of you really caught on to that. Not everybody, and that's okay, because some of your explanations maybe weren't exactly what I was thinking, but you still were able to relate it really well to the content. Cassidy, however, really picked up on it. This is a humorous representation. So humorous being, it's a Lord of the Ring reference. This is like our little Gollum, you know, my precious. I can't do Gollum's voice. I won't try. I won't embarrass myself. Where water has, attract electrons more strongly. So oxygen has a higher electronegativity. So it's like there's a tug of war. Oxygen doesn't win. It doesn't completely steal. Water is not ionic, remember. But there's a tug of war going on, and oxygen is stronger in that tug of war. And so that's what ends up making the oxygen side. And this, we know there's a limitation to our comic, and we don't have the two hydrogens, but we're only focusing on one of those bonds, one hydrogen-oxygen bond. And Cassidy, this was a great answer. I was really searching, looking for these exact kind of terms, and you just did phenomenal there. So oxygen has higher electronegativity, so those electrons aren't shared equally, and that's what causes that polarity of water, which caused the water to move in the previous demo. So this question is really getting at common misconceptions about physical phenomenon. So probably all of you have seen this kind of situation. And if you went to like a Yahoo message board and asked the question, you'd probably get lots of different responses. In fact, some of these might come up. And you guys, some people thought one thing in the beginning and thought another in the end. For example, the student I chose here was Gavin. Originally, Gavin had just kind of guessed at D, and I like that. And that's okay with those initial responses. It's just about getting your brain thinking. But Gavin, by the end of the week, realized the correct answer is actually B. It's the air on the outside of the glass. There is water vapor in the air. You can't see it, but there's water all over the place. But when it comes in contact with the cold glass, there's an energy transfer. It passes energy to the glass, which means then it's going to lose energy and slow down, and condensation happens. So it is a gas that turns into a liquid. So excellent job there, Gavin, on recognizing, it's okay to guess, but recognizing that correct answer after, and really being able to relate this to the content. We want to see that phase changes happen because of energy transfer. And if energy is going in, so that endothermic, surroundings lose energy and their temperature goes down, but this substance has phase change and maybe their temperature goes up if they gain enough energy. If energy is going out, we have a different kind of phase change. We have those exothermic ones. So nice job relating that to the content as well. So what's next? Again, we're actually going to continue talking about water quite a bit, not just water, but water is a good one for talking about. We're going to look at more about water. We're actually going to learn a couple more reasons why water is essential to life on Earth, besides those original two we learned from the reading. For example, we're even just going to learn, why does water stay in the liquid phase so well? Because not every substance does that. We're going to learn about dissolving, what's really happening at the atomic, the molecular level. You could zoom into the Miss Frizzle level, what's really going on. And then one of my favorites, the action of soap, because every single one of us uses soap. So that's a way that chemistry is in our everyday life. So we're going to talk about why does soap work and what's really going on at the atomic level. So our Unit 3 test does open up this week, so be prepared and ready to go for that. Remember, our tests are open note and open book, but you don't want to be finding out where that is in your book or where that is even in your notes during the test, because they are timed and you do not have enough time to look up every answer. So be prepared. We do have some extra credit opportunities this week. We have the one we always have with a test, which is putting your questions on the test prep discussion board early enough. If you're not sure what I'm talking about, just review the directions for the Unit 3 test prep discussion board. And then there is an Easter egg in our checklist, like a literal image of an Easter egg. So if you have something hidden, like in a video game, it's called an Easter egg. So what I've done is I've put a literal picture of an Easter egg, and if you click on it, it is actually a link to something else. So when you go and look at that, I want you to think, how does this relate to the content? And then I'm going to ask you, kind of what was your favorite part, etc. So there's going to be a question on the upcoming test related to that Easter egg link. And remember, extra credit test questions are worth more than generic extra credit. So you get a little